We talked about the first part where we looked at emergent risks from climate change and of course population change and migrations and human movements and globally connected economy and so on. We talked about vulnerability and physical and socioeconomic vulnerabilities and risks and so on. In part 2, we are going to move into health consequences of climate change, starting with changes in hydrology and its impacts on waterborne diseases. Obviously, a very critical part of the health outcomes and planetary health, especially in the deep tropics and global south, where warm temperatures tend to make the waters full of microbes. The populations of the global south tend to be immune to a lot of the microbes in the water. For example, people coming from mid-latitudes and out from developing world into the tropical countries tend to get sick because they are not host to those bacteria in their stomach. But that doesn't mean you can be immune to everything. Typhoid, salmonellosis, campylobacteriosis, we'll talk of many diseases that affect everybody. So you cannot be immune to everything. Just to get a brief introduction to the hydrologic cycle so that we can later on think about how processes affect waterborne diseases and the pathogens. We can look at the basic processes. This is hydrologic cycle, or the water cycle is part of the energy being moved from energy excess regions of low latitudes, where you remember more sunshine or energy from the sun is received than is lost to space, and to the polar regions where there is an energy deficit because more energy is being lost to space than is being received from the sun. So this constant movement of energy is done by winds and cyclones, hurricanes, ocean currents and so on. But dry air cannot carry much energy. It doesn't have much density or heat capacity, so water is key ingredient. The low latitudes, warm regions evaporate a lot of water from the oceans, of course, and from land as well, and it condenses in the atmosphere. Almost all of it falls back in the low latitudes, but some fraction of it is carried poleward in both hemispheres, which is what the water cycle is a lot about. And the processes of evaporation and evaporation mediated by vegetation called transpiration are giving energy to the atmosphere. That condensation is driving the circulation and moving heat and water to the higher latitudes. The fraction of precipitation that happens on land as snow and rain and so on obviously either collects as glaciers on land or sea ice in the Arctic and so on, or it makes it as surface runoff, infiltration into groundwater, river runoff, and groundwater flow into the water bodies and eventually into the ocean on various time scales. Higher latitudes, as it gets colder, the cold air cannot hold much water vapor, so water vapor is being brought in from lower latitudes to higher latitudes. The snowfall rates can be tiny, but over long times they can obviously build kilometers thick glaciers on Antarctica and Greenland and so on. So part of the global warming, of course, is that if you melt those shiny surfaces like snow, glacier, sea ice, you're going to reduce reflectivity of the sunlight and you're going to absorb more energy, which is going to make it even warmer and melt glaciers and sea ice even further and snow even further. But snowmelt can also change the river flow seasonality. Instead of, for example, peaking in spring, they can begin to peak earlier, and that affects the ecosystems in the rivers, estuaries, and coastal oceans greatly when you change those seasonalities, because the life that is present in those regions have evolved over time to time their spawning, their recruitment, their life cycles to these natural variability in runoff, coastal salinity, oxygen, nutrient flows, and so on and so forth. But those are also the processes that will affect the pathogens that are of interest for us, especially when you combine with land use change, nutrition, nutrients running off from agriculture, urbanization, and so on and so forth. This is a detailed image that is showing a radar diagram of climatic determinants of waterborne pathogens, air temperature, water temperature, precipitation, and heavy rainfall event by pathogen from climate change knowledge base for food and waterborne diseases over this period of 1998 to 2009. So note that terms air temperature, water temperature, precipitation, and heavy rainfall event have been extracted from peer-reviewed literature for the individual pathogens listed. So basically they take all the papers they can find and map onto these spaces, and this diagram basically has multiple links, axes emerging from common origins, showing the various links. The first one of these shows waterborne diseases and pathogens related to water use, like irrigation, food production, dairy products, and the various timescales and the processes like winds, UV light, sunshine hours, relative humidity, extreme events, precipitation, water temperatures, air temperatures, climate and environment, and so on. The second of these will show the extreme events, which we'll come to after we go through some of these. So you can see the various relations. Obviously we will not go through all of these, but you can look at the range of things here. Meat and meat products to fish and fish products to sauces, salads, spices, fruits, fresh fruit, vegetables, confectionery, bakery items, sweeteners, dairy products, and so on, to usage, so tap water, bottled water, recreational water, food production, irrigation, and water bodies like groundwater, surface water, and so on, to contamination processes, sewer overflow, diffuse feces, wastewater, to pathogens, bacteria, and including Campylobacter, Salmonella, Listeria, non-cholera Vibrio species, viruses, enterovirus, Cryptosporidium, and so on, to the processes, changes in temperature, minimum temperatures, average temperatures, and so on, up to here seasonalities, changes in seasonal patterns, and so on. So you can see the various different links that exist, and there are also these gray regions with other links being shown here. Okay, this is a good map to have in terms of knowing what are the various links that are already known and how they are changing over time. If you have a baseline, then you can keep mapping changes onto these as well. And also when you look at the extreme events, for example, again you have the food items that we talked about, usages that we talked about, parasites and bacteria that we talked about, the processes that we talked about here, including snowmelt, heavy rainfall events, storms, droughts, foods, extreme events, changes in precipitation patterns, changes in precipitation itself, and so on and so forth. Okay, so here we are going to look at change in frequency, change in wind direction, change in wind strength, change in cloud coverage, and so on and so forth. Okay, again, a good map to have in terms of what are all the data sets used, what are all the methodologies used, what are all the links that are already made, and how these links may be changing over time. This is another radar diagram looking at the number of studies with different linkages of air temperature, water temperature, heavy rainfall event, and precipitation for norovirus, Vibrio non-cholerae. So we'll talk about this later on, but basically you have Vibrio cholerae, Vibrio parahemolyticus, and Vibrio vulnificus. Okay, so Vibrio cholerae is very dominant in warm tropical waters, whereas Vibrio parahemolyticus and vulnificus are present in colder mid-latitude, high-latitude waters. Okay, Campylobacteriosis, Salmonellosis, Cryptosporidiosis, and you can see the number of studies. There is linking air temperature and Vibrio non-cholera, Campylobacteriosis, Salmonellosis, not so much on norovirus and Cryptosporidiosis. water temperatures themselves, highly correlated with campylobacteriosis in the number of studies and Vibrio non-cholerae, but not so much on these end. Heavy rainfall events, small amounts on Vibrio non-cholerae here, but not so much in the other regions, even though these are just based on what studies have been done during this period of 1998 to 2009. Okay, please remember that. Obviously, new studies keep coming, and now there is evidence that extreme rainfall events do affect salmonellosis, especially going from the coastline to the inland for some regions of the Chesapeake Bay watershed, for example. Okay, precipitation, again, relations found for various of these waterborne diseases. Okay, I'll leave this here, and we will add another podcast looking at more specifically the impacts, the cascades of hydrological processes into health outcomes, and some of the typical bacteria that we have to worry about when it comes to waterborne diseases. Okay.